Hey everybody, welcome to chapter 10 on regression. And this is basically just taking bivariate correlations, which we did in the last chapter, which are just associations between two variables. This is just taking that one step further. So we're still going to be talking about, in this chapter, how two variables are related, but we're also going to fit a line of best fit between the relationship between those variables, and that actually will allow us to predict, hey, if I have let's say, I don't know, somebody who is 6'4", I can predict based on how tall they are, how much they ought to weigh also. So we can actually start to use regression to use one of the variables to actually predict values of the other variable, which can be very handy. So now regression tells you about the relationship between two variables, but you can even go beyond that to see whether you can use the value of one variable to predict the value of the second variable. In other words, can you use a participant's score on one of the variables to predict what their score on the other variable would be, even if they haven't completed that variable? Like, for example, if they study 4 hours a week, can you predict what grade they'll get on the final exam, even if they haven't actually taken the exam yet? And this has real world applications because, for instance, like university admissions boards, they'll take your high school GPA and SAT or ACT scores, and they'll actually try to predict based on those scores how well you're going to do in college and whether they should admit you or not, basically. You see this all the time also in like sales and marketing with, well, how much money should we spend in order to get a good return on that investment? And employers sometimes will do this with various different kinds of personality tests or whatever to try to predict how well a person will do in that role. And so if you consider the scatter plots that we created during those correlation tests, and you imagine trying to fit a line that goes through or as close to as many possible points as you can from a scatter plot, regression is actually making the equation for that line of best fit. And then what you can do is you use that line of best fit to say, okay, well, if I, score a 25 on my ACT, which we could say is like the x-axis variable, what might I predict is my college GPA, let's say that's on the y-axis. Okay, so let's walk through how this kind of works. So remember way back to probably high school, maybe before high school, when you're actually coming up with a equation for a single line on an x and y coordinate plane, right? That would be y equals mx plus b is probably what you remember it. Well, this is the same thing. Y, which is going to be a single observation for the outcome, equals x, which is a single observation of the predictor variable, the independent variable, times the slope, and then you add the y-intercept. Your book uses these terms, y equals xb plus a. This is the exact same thing as y equals mx plus b, but unfortunately those letters get flip-flopped a little bit. So y, again, is a score on the y variable, x is a score on the x variable. The slope is, of course, rise over run, right? The amount of slant that a line has, and that's going to be represented by b. And then the y-intercept is a, and that is the value of y, where this line of best fit crosses the y-axis. So you can see on this graph, there's a few points scattered throughout. This looks like a pretty positive, strong positive correlation. And then if you fit a line that goes as close as possible and touches as many possible of those points or observations as you can, you end up with this line of best fit, which is y equals 0.95, that's the slope, 0.95, x plus 9.4. So it looks like we're looking at arm span as the x-axis or the predictor variable, predicting height, which is the y-axis and y variable. And so you could say, okay, 9.4, I'm going to guess, oh yeah, these are in centimeters, 9.4 is where the y, where this line would cross 0 in terms of arm span of centimeters. That's where the y-axis is where x equals 0. But of course, nobody is 9.4 centimeters tall, at least to my knowledge. So we've got to introduce just a little bit of new mathematical notation here, which is a very fun one. It's called y hat. We literally call it y hat. Looks like it's got a little boomerang or something on the top of it. Y hat is not now a real value of y, meaning the outcome or the dependent variable at a certain value of x. It's the predicted value of y at a specific value of x. Predicted. So you can see on the line of best fit in this figure, the line passes through some points, but also there's parts where there's just the line there, and there's no actual data. But what this allows us to do is to say, well, what would I predict the y score to be if I know I have an x value of, I don't know, let's find a little thing, 200 centimeters, an arm span of 200 centimeters. Well, the predicted height looks like 200 centimeters. You go over to the x-axis, 200. You follow that all the way up to the line, and then you say, well, what number on the y-axis does that correspond to? It looks like also 200. So 200 centimeters in terms of height would be predicted from 200 centimeters of arm span. At least that's what it looks like, even though there's not really a point there. So that's why y hat is the predicted value of y. And actually, since we have the equation for the line of best fit, why don't we just figure out what is the predicted value of y, that is the predicted value of height, when arm span equals exactly 200 centimeters. Based on this data, we have the line of best fit that says y equals 0.95x plus 9.4. So we just plug into that equation, 200 centimeters is x. So you say 0.95 times 200 plus 9.4, the y-intercept, all of that equals 199.4. So we can say that y hat, we can predict somebody's height should be 199.4 centimeters if their arm span is 200 centimeters. So when do we actually use linear regression? It's called linear regression, even though most of the time people just refer to it as regression, but that gives you a little hint. You have to have two numeric variables. You can't have any categorical data, at least not that we're going to be covering. So you definitely want both of the variables to be numeric, and you use linear regression when you want to test a linear relationship between the two variables, as the name suggests. But we also saw that with correlation. So this is, again, one step further. If you want to see if the scores on one variable would be a significant predictor of scores on another variable. So for instance, you might have a research question like, does amount of sleep have some kind of effect on exam scores? And could we actually use hours of sleep to predict exam scores? Now that would be interesting. You've probably also heard of something like using years of education to predict the amount of money that you would make later in your career. So higher amounts of education we might predict would also be associated or predict higher earnings, right? That makes sense. So you've probably heard of that kind of stuff. We use linear regression all the time in psychology. So it is definitely something worth your time. Let's dive into it. Okay, so let's take an example, and maybe you can relate to this example. I would be curious to try to predict your stress level, or anybody's stress level, using weeks since last vacation. So we might expect, if you haven't had a vacation in a lot of weeks, that your stress level might increase. And then from there, we could actually say, well, if I know the amount of weeks since my last vacation, let's say it's 8 or something like that, or 34, what level of stress would we predict? So our X variable, our predictor variable, is weeks since vacation, and our Y variable, our outcome variable, is going to be stress. And where we're headed with all this is we need to ultimately find the equation for a line that represents the relationship between weeks since last vacation and stress. So the whole point of this is to figure out the equation for this line. And we're going to start actually with the slope. We're going to try to calculate the slope, but we're going to have to do a couple things on the way there. Well, you remember back to last chapter when we were talking about correlations and first needing to calculate the covariance between the two variables. Well, guess what? We do exactly the same thing for linear regression. So first we're going to calculate the covariance between weeks since last vacation and stress. So you already know how to do this. We're going to take all of the participant scores on X. X is, again, our predictor variable, so that's going to be weeks since last vacation. We're going to subtract them all from the mean of X, the average weeks since last vacation, so that's going to give us all of the deviations of X. We're also going to get all the deviation scores for Y, for stress. Everybody's stress, Y bar is the average stress of the entire sample. We subtract each individual person's raw score from that to find all the deviations. We multiply the deviations of X times the deviations of Y, and then we add up all of those products. We add up all of the products of every individual, and then we divide all that stuff by n minus 1, the number of participants minus 1. So the first thing you have to do is calculate the mean for X and Y, which you can find very easily. The mean weeks since last vacation for this sample is 5 weeks since last vacation. The mean stress level is 7.6. So now that we have those, we need to find all of the deviation scores for X and Y for each of the participants. And we could do this by hand, obviously, like we had to do with standard deviation, but might as well let Excel help you out, or whatever program you choose. But we can see now that the deviations for weeks and the deviations of stress, we've just taken all of the individual raw scores for each participant for, let's say, the weeks. We've divided, or rather, we've subtracted the mean, the average weeks, out of that. So 5 minus 5 gives us a deviation of 0. 3 minus 5 gives -2. 10 minus 5 gives 5, and so on. For stress, the mean was 7.6, so we take 10 minus 7.6 is 2.4. 6 minus 7.6 is -1.6, and so on and so forth. And we've got our deviation scores, but now, of course, we need to get the products of each of those X and Y deviation scores for each participant. So a new column over here is the deviation products, where I would have multiplied, let's take the first participant. I would have multiplied their deviation of weeks of 0 times their deviation for stress, which was 2.4, and that would give the deviation product of 0. Participant 2, you take the deviation score for weeks, -2, multiplied by the deviation for stress, -1.6. -2 times -1.6 is 3.2. And you keep going down the list. And finally, once we have all those deviation products, we need to find the sum of those deviation products. That's the numerator for covariance. So we found a sum of 32. But now we need to divide by n minus 1, number of people in the sample minus 1. So there's 5 people in the sample, minus 1 is 4, so we're going to end up with a final covariance of 8. 32 divided by 4 gives us 8. So that is our covariance. Okay, so why did we have to calculate the covariance? Well, the covariance can then get you to the slope. So we can finally actually calculate the slope. Next, we'll be moving on to calculate the intercept, And then finally, we'll be ready to have our line of best fit for this data, and we can then predict any value of stress from any value of weeks since last vacation. So what is this equation right here? This is the slope, B, equals the covariance of x and y, which we just found, divided by the variance of x. S squared, S, you will remember, is standard deviation. Standard deviation is the square root of the variance. But S squared, so it has not been square rooted yet, S squared is the symbol for variance. So what we're looking at is the covariance of x and y divided by the variance of x. And you could just use Excel again instead of having to do all the stuff by hand. You type in equals VAR dot S because it's a sample. If it was a population, you would use VAR dot P, but variance equals VAR dot S, and then you click on all of the values for weeks since last vacation, and you find out the variance of x is 11.5. So to find the slope, we just take the covariance, which we found was 8. We divide it by the variance of x, which we found just now to be 11.5. And you end up with a slope of 0.70. Okay, so what does that mean in practical terms or in kind of layman's English? What it means is that for every 1 week that passes since your last vacation, so every additional week, your stress level increases by 0.70. So for every week that passes since your last vacation, your stress level increases by 0.70. So the slope is all about a 1 unit increase in the x variable yields what kind of change in the y variable. It could be negative, right? Slopes can be negative or they can be positive. In this case, it's positive, and so that means that as more weeks go by, stress increases. If it was negative, it would say as more weeks go by, stress decreases. But that's not what we're seeing here, right? Okay, so we've got the slope. Now we've got to figure out what is the y-intercept. And this one's pretty easy, at least. The y-intercept, which we call A, equals the mean of y minus the slope times the mean of x. Well, good news. We've already calculated all those numbers, so it should be pretty simple to get the y-intercept. So we've got the mean of y bar. That's the mean of stress for all of our participants. That was 7.6. We're going to subtract slope times the mean of x. The slope was 0.70, and the mean of x, our predictor variable, which is weeks since last vacation, the mean of that was 5. So we end up with this equation, 7.6 minus the product of 0.70 times 5. And when you do the math, you find out that the y-intercept is 4.1. 4.1 what? Well, what is the y-intercept? Conceptually, the y-intercept is the value of y when x equals 0. So this is the value of stress if there is no weeks since last vacation. So if you've just had your vacation, or you're on your vacation, I guess, then your stress level, we would predict, would be 4.1. If you have had 0 weeks since your last vacation, so you're either on your vacation or maybe just coming off your vacation, your stress level would be 4.1. All right, beautiful. Now we've got the equation for the line. We've got the predicted value of y hat, equals 0.70, the slope, times x plus 4.1. This is the equation for the line. And so now we can say, if I have a particular value of x, remember x being the number of weeks since last vacation, if I have a particular value for x, well, then we can just plug that in and get the predicted value of y. So here is my question to you. If the value of x, the number of weeks since your last vacation, was 8 weeks, what would you predict your stress level to be? Well, if you did the math, you should have gotten an answer of 9.7. We would expect that after 8 weeks of not having vacation, your stress level would be 9.7. Now here's the thing, right? Like, if you found yourself 8 weeks after your last vacation, we don't know with any particular certainty that your stress level would be exactly 9.7. We're saying based on the data, based on the people that we have in this study, the 5 participants who gave us their data, based on their data, we would predict that someone else who's very similar to those people would have a predicted stress level of 9.7 after 8 weeks of not having vacation. That's not the same thing as saying you definitely will have exactly a stress level of 9.7 after 8 weeks. These things are all about predictions. And of course, when you predict things, there's always going to be some room for error. So check this out. This is you can have Excel or other programs actually create what's called a trend line or a prediction line. In this case, we're talking about the line of best fit, and we already found the equation for it. Y equals a slope of 0.70 times x plus 4.1, right? This is that line, and it's you can see that the 5 different data points are there. Each of these data points represents one single person's score on both the x variable, which is weeks since vacation, and the y variable, which is their stress. You can see in general the trend line is going up and to the right, which means that these two things are going to be positively related. So as weeks since vacation increases, stress also tends to increase, especially you can see along this line. I have no idea why the trend line doesn't actually cross the y-axis, because the y-intercept is the value of y when x equals 0. So the dots should go all the way to the y-axis. I think because we don't have any data points at 0, Excel just doesn't know how to extrapolate, which is kind of silly. But disregard that. The line should be continuous, basically, all the way from the left side of the graph towards the right side of the graph. Okay, so what I've done here is basically created a visual representation of how you find the predicted value of y for any given value of x. We were talking about a value of weeks since last vacation of 8, right? So 8 weeks since last vacation. So if you go to the x-axis, the horizontal axis, and you find weeks since vacation of the number 8, and you follow it up to the trend line, and then you stop right there where it touches the trend line, and then you go immediately all the way to the left to figure out where does that line up on the y-axis. Well, we already know that, right? It's going to be 9.7 because we already did the math and found that using this equation for the line, that if you have 8 weeks since your last vacation, we would predict a value of 9.7 for your stress level. And so you can see that just visually represented here. Hopefully that helps. All right, that's it for this video. Hope you enjoy this little meme. It is true that oftentimes we don't get super strong correlations between variables, and so the nice scatter plot points that you see in this top graph, it's very rare that you see variables that highly and tightly correlated or related at all. More so we get things a lot more spread out. Humans are very messy, and they have all kinds of differences and uniquenesses which is also fun, obviously, right? But this bottom panel is showing you what if you have an outlier, and then it can just absolutely crank on the trend line to change it by quite a bit. So I hope you enjoy. I'll see you in the next video.